So section 4 is energy in simple harmonic motion. Remember, SHM is simple harmonic motion. So we have basically already talked about this before, so I'm going to kind of glaze over a little bit. When the mass is at its extreme point here and here, its velocity is 0. It's turning around and starting to go the other way. So therefore, its kinetic energy at those points would be 0 because its velocity is 0. And it would have maximum potential energy. Likewise, when it's passing through the equilibrium point right there, in either direction, that's where its velocity would be maximum, and it has converted all of its potential energy into kinetic energy. Make sense? Okay. So as the object passes through equilibrium, the energy is purely kinetic. If the object has a mass m with spring constant k, then the potential energy at the extreme ends is 1/2 times k times x squared, the position x being one side or the other. It doesn't matter if it's positive or negative, it just winds up squared anyway. Okay? So if the surface is frictionless, then there is no energy loss. So this thing will just keep oscillating back and forth. So that means we have a constant, a horizontal energy line, and then k only plus u only. And so since k is 1/2 mv squared, we have that. And then since u is 1/2 kx squared, then we have that. So this is our energy equation now. Okay? And from that, we can make a graph. So, energy changes for a playground swing. You're at the playground undergoing a simple harmonic motion on a swing. Describe the changes in energy that occur during one cycle of motion, starting from when you are at the farthest point forward, motionless, and then through just about to swing backward. Okay? So, we have it's basically a pendulum that we're talking about. So we have our swing on this over here, we have our swing over here, and this thing just oscillates back and forth, right? So it says describe the changes in energy that occur. So what are we going to say here? What are we going to do? Nothing?
Just skip the problem.
We don't know anything?
Does it want to, should we graph it? Graph the energy?
You want to make an energy graph? That's probably the best way to do it.
Mr. Blister.
So if we just go straight to an energy graph, then we have this. What's the horizontal axis?
Our motion.
So is it X, is it Y?
I would say X.
X, okay. And then what's on the vertical axis?
Our energy.
Yeah, it's an energy graph, so there we go. Now, in this system where this person is going back and forth, you're going to have a total energy line. What's that going to look like?
A kind of parabolic.
The total energy line?
Oh, sorry, never, not the total.
It's just another horizontal.
It's a horizontal line. So whatever our total energy is would be there. Okay. Now what?
Now we can put in our potential energy line.
Okay, a potential energy curve of some sort. So if that's what we're going to do, then where do I start this curve?
Where we start, we have.
Do it above the line.
We do?
Because we have only potential.
Oh, this is potential.
So as of right now, if we're at the extreme end over here, do we have a lot of potential energy or a lot of kinetic energy?
Potential.
Potential energy. So we would be using all of our energy on potential energy right now.
Can I take my business period and arms?
Yeah. So now what's going to happen as we swing through? Like when we get to this point right here, what's going on?
It's going to be
Maximum kinetic.
Maximum kinetic, which means how much potential?
0.
No potential. So right here at the equilibrium, we are at the bottom of potential. And then what happens?
It'll go back up to the total energy line.
Yes,
Back up to the top.
correct. So back up to here. And then is this just connect the dots? We're going to draw line segments, or are we drawing a parabola, or what are we doing? Parabola?
Yeah. And it goes all the way to the.
Oh, what's wrong with this?
It goes below the graph.
Yep, so we definitely don't want to do that. If this was the AP exam, they would take points away for that. So we want to hit 0 for sure. There you go. And what is this curve?
A parabola.
No, I mean, like, what am I going to label it?
Potential energy.
Potential energy.
So if like the graphite was bordering so closely that there's no white between them, is that okay?
Yeah, you're okay.
Okay.
Yeah. And then if it overlapped a little bit, I might just erase it and redo it. But you definitely don't want to go under, okay? Because the interpreter on that is not going to be like, oh, they didn't mean to go under. They just sort of did, and it's okay. They're just going to mark it wrong because they don't know if you meant to do it or not. Okay, so normally we do not draw a kinetic energy curve on here. But if I did, what would it look like?
It'd look like the opposite.
Yeah, it would be the opposite. So at the beginning, we have no kinetic energy. In the middle, we have maximum kinetic energy. And then at the end, we have no kinetic energy again. So once again, I don't want to go above that curve, so I'm very careful as I get up there. That's what the kinetic energy would look like. So I know I wrote PE, but usually we would just write U because that's and then K for kinetic. Okay, so like I said, previously we did not do this kinetic energy curve. The kinetic energy is the difference between the total energy and the potential energy that we've used. Okay, so that's a pretty good description right there. Now, simple harmonic motion frequency. So I'm just going straight to it right here. This is the frequency in the period for simple harmonic motion for a mass M on a spring with this spring constant K. So remember that period is the reciprocal of frequency. So if you take a good look at this, you would see that they are just reciprocals of each other. 1 over 2 pi square root K over M. Reciprocal becomes 2 pi over 1 square root M over K. Okay? So pretty straightforward there. But notice what these formulas imply. The frequency and the period are determined by just the physical properties of the oscillator, which is in this case a spring, mass, and the spring constant. That's it. That means that the frequency and the period do not depend on the amplitude of the wave that you're talking about. Okay? That's actually really important to know. So now this figure down at the bottom, the frequency dependence on mass and spring stiffness. So if I have a high frequency, I could have a stiff spring or a low mass. If I have a low frequency, I could have a soft spring or a high mass. So the more I stiffen the spring, what does that do to my frequency? I stiffen the spring so that numerator becomes bigger, so that result becomes bigger, okay? If I increase the mass is in the denominator for frequency. So if I increase the mass, that makes the fraction that I'm square rooting smaller. So I wind up with a smaller frequency, a smaller number for the frequency, okay? So increasing the mass does what? Speeds it up or slows it down?
That would slow it down for frequency.
Increasing the mass slows it down, yeah. Okay, so here we go. An astronaut measures her mass each day by using the body mass measurement device. So it says as described on the left, which I don't have. So basically what the body mass measurement device does is it uses a spring oscillator. So an astronaut will sit in a chair or something attached to a spring, and this thing is going to oscillate back and forth. It's going to have a frequency to it, okay? Now, during an 8-day flight, her mass steadily decreases. So what is going to happen to the oscillation on this body mass measuring device? What's going to happen to the frequency there?
It's going to increase.
It's going to increase. It's going to speed up because she's losing mass, okay? So as the mass changes, the frequency changes. So how does this change the frequency of our oscillatory motion on the device? That's basically all we're going to say. The frequency of the oscillations is going to speed up because she is losing mass. We don't have any numbers here to plug in and calculate, so we just do a description using that concept. The K, the spring, a constant, doesn't change because it's the same spring the whole time during the flight. Okay, so now here's your strategy box, identifying and analyzing simple harmonic motion So the first thing we do, if the net force acting on the particle is linear restoring force, then the motion is simple harmonic motion around the particle's equilibrium position. The velocity, position, velocity, and acceleration as a function of time are given. I already gave you those. The equations are given in terms of x, but they can be written in terms of y or theta or some other variable if the situation calls for it. The amplitude is the maximum value of the displacement from equilibrium. We know that already. The maximum speed and the maximum magnitude of the acceleration are also already given to you. The frequency, and hence the period, depends on the physical properties like we just talked about, but does not depend on the amplitude of the wave itself. So for the mass on a spring, the frequency is given by this formula that I just gave you. And then finally, the sum of the potential energy and kinetic energy is constant as long as there's no friction. As the oscillation proceeds, energy is transformed from kinetic to potential and from potential to kinetic and back and forth forever. Okay? All right, so finding the frequency of a mass hanging from a spring. So a spring has an unstretched length of 10 centimeters. So let's go ahead and switch that right away. 0.1 meters. A 25 gram mass, so again right away, 0.025 kilograms. Hung from the spring, stretching it up to a length of 15 centimeters. Okay, so we switch that, 0.15 meters. If the mass is pulled down and released so that it oscillates, what will be the frequency of the oscillation? Okay, so remember that we have this delta L situation right here. So the normal unstretched length of this spring is 10 centimeters, but then we add the mass and it deflects the spring down to 15 centimeters total. So now when I pull on this spring or push up on the spring with that mass added there, the equilibrium position is no longer 10 centimeters, it's down here at 15 centimeters, okay? So we have that delta L that we have to contend with. So now what do we do if I'm trying to calculate frequency? So if we use the delta L equals mg over k, what are we looking for here?
Okay.
K. So I'm going to multiply both sides by k, divide both sides by delta L, and now I have k equals mg over delta L. Do I know all of those things?
Yes.
Yeah. So we can now calculate k. Now that I know k, and I know m, and I'm supposed to calculate the frequency, what should I do?
We can plug it into our frequency formula.
Our frequency formula is F equals, what is it?
1 over 2 pi
Okay.
times the square root of k over m.
K over m on this one. Okay, so, but k is mg over delta L, right? So I can swap that in. I have 1 over 2 pi times the square root of, now k is mg over delta L, and this is all over the mass. What happens?
The mass divides out.
The mass divides out. So I don't have a denominator of the fraction anymore, and I just have 1 over 2 pi square root g, which is 9.8 meters per second squared, divide by delta L. What is our delta L?
0.05 meters.
0.05. That's the delta L right there. So 0.05 meters. Okay, what do we get?
I got 2.2817.
2.817, what?
Hertz in their seconds.
Yeah, so meters divided by meters and the square root is gone. So I have per second squared, but it's square rooted. So it's per second. So this would be inverse seconds, and which is 1 hertz. So do we like this answer right here?
No.
What do we like?
2 probably?
2 points.
2.2.
Yeah, let's keep 2 significant figures. So this, in this case, would be 2.3 hertz. Okay, good. A gymnast jumps on a springboard. So in the vault event, the gymnast begins her routine by jumping on a springboard. You can see the springboard right there. If you've ever watched Olympics, you know that. A platform with springs underneath. In one vault, a 45-kilogram gymnast jumps 0.6 meters above the springboard's surface. She then lands on the springboard, which compresses it. What is the maximum compression of the springboard? How much time does it take for the board to fully compress? The spring constant of the board is 50,000 newtons per meter. Okay, so what are we looking for here?
The delta L.
We're looking for delta L, it seems like, yeah. Maximum compression, delta L. Or would it actually be the amplitude of the wave? So delta L is a deflection when we add a mass. The amplitude is how much the spring goes back and forth from equilibrium. So which one is it?
The maximum compression.
We're adding mass, but it's replacing the wave.
I think it's the amplitude that we're looking for, right? Okay, so instead of that, I'm gonna write, I want the amplitude. Okay, how much time does it take for the board to fully compress? So we're looking for what there?
Time.
Like a delta T? Okay, so in this situation, I can draw a picture. We have the initial height of, or the highest height, and then down here is the springboard with springs underneath it. Okay, so what is this height right here? The gymnast jumps 0.6 meters above.
Oh, so just be.
So 0.6 meters, okay. And what else do we know?
The mass of the gymnast.
Okay. Mass is 45 kilograms. What else do we know?
The spring constant.
Okay, we know the spring constant, K, is crazy, 50,000 newtons per meter. What else do we know? What about velocity? Do we know anything about velocity of the gymnast?
I don't believe so.
No.
But does it, you mean like vertical velocity, like how?
Yeah,
fast you
so like
go?
Y, a VY initial or VY final? Do we know either of those?
Well, we know her height, we know her mass, and G.
How does she get to that height?
Like jump?
She jumps. So she's like running along and then she jumps and then she lands on the springboard and she gets vaulted off, right? So VY initial would be from this height right here, which is 0.6 meters. So what is VY initial?
Oh,
The velocity in the Y direction?
oh.
Oh,
if
zero,
it's
'cause
at-
that's her
yeah,
peak.
It would be 0, yeah. So the velocity here, VY initial, is 0 meters per second. I don't know what we need here, but you know, we do know that, right? Okay, we don't know the final velocity at the end, obviously, but we do know her acceleration. It's due to gravity. Okay, so this is the before picture. Now the after picture. So here we are, and now she's compressed the springs, and she's on the board. So what do we know here? Like Y final, she's at 0 meters. What else do we know? Her mass is still 45, right? Hopefully.
Yeah,
Anything else we know?
the spring constant.
K is still 50,000 newtons per meter. Anything else we know?
Could we calculate her velocity in the Y direction? Or that would be, well, we could calculate it easily as she made contact with the springboard.
So we could calculate her velocity in the Y direction once she hits the springboard, yeah. But now she's depressed this, right? Like originally that springboard was up here and now the springs are compressed. So this would be like Y final here. would be the same as the initial like equilibrium point for the springs, right? And now we've compressed the springs down. What does it say? Does it say anything about that? Nope, it just says which compresses it. So we're gonna compress the springs down here. We started right here and then we compressed them a distance. What letter do you want to use for compressing the spring? X, because that's the letter we always use. Okay, so this is the distance X right here. Okay? All right, let's see. What can we do? So let's look at the energy of this. What do we have?
Spring potential.
Spring potential. What do we, so once we load up the spring, it has potential energy, right? Okay, so what would that look like? What should I say there? Let's just start basic. Potential, spring. What else do we have?
The gymnast has kinetic energy.
In the beginning or at the end?
In the beginning, well, when she makes contact with the spring.
Okay, but in the beginning, there's potential, right? So that would be potential gravitational. Final and gravitational initial. So over here, initial gravitation potential energy would be what? mg y initial. Okay, over here, the spring potential energy, once we load it up, would be what?
1/2 kx.
1/2 kx squared?
It is squared.
Okay. And then what's this gravitation potential final?
That would just be mgy final.
Okay. Now what?
Now we can solve for x.
All right, so let's say I solve for x. I move this guy over here. mg can be factored out, and I just have y initial minus y final. And then I'm going to multiply everything by 2, and then divide everything by k, and then square root everything, and I wind up with x. So now what?
Now we can plug in what we know.
What do we know?
Well, we know her mass, 45 kilograms.
Okay.
Y initial is 0.6 meters. And then Y final, what would Y final be? Do we know that?
0.
Is it? Okay, so then there would be, well, but then there would be no potential gravity final.
So what are we doing?
Because she.
Oh, well, would Y final be 0.6 meters plus whatever x is?
Y final is the same as x initial, don't you think?
So at the equilibrium point?
So it's like x. It's like having another x.
Oh dear, okay.
Yeah, so maybe we can't do this so simply. Maybe we need to treat this right here as an x, and then move this guy over, and now we have a quadratic equation.
Okay.
So let's do that. So I'm going to erase this. Okay, so actually what's happening here is this guy is gonna move over because y final is the same as x basically. So we have 1/2 times the spring constant, which is a number, x squared, plus mg times x, so mg is just a number, and then I subtract mg y initial, which is all constant, equals 0. So I have a quadratic form here. So to solve this, I could use the quadratic equation. So the quadratic equation, remember, is x equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. So now we can plug in these numbers. So we have x equals negative b, so that's negative mg, and then plus or minus the square root of course, the plus or minus here might not matter, but b squared, so that's going to be mg squared, minus 4 times a, which is 1/2 k, times c, which is negative mg, all divided by 2 times a, so 2 times 1/2 k is just k. Okay, so at this point now we can just plug in the numbers that we see. With the exception of this plus or minus right here, we have to think about that for a second. Should we use the plus? Should we use the minus? Is it one or the other? Is it both? What should x be? Positive or negative?
Negative.
I don't know. Maybe we want the same answer both ways. Who knows? But let's plug in the numbers and see what happens. So negative mg, we have x equals negative mg. What do we got? Like around 450 newtons. So negative 450, I'm just going to write it down, negative 450 newtons, plus or minus the square root of. Now mg is 450 again, but we got to square it. I don't know what that is off the top of my head. Minus 4 times 0.5 k times negative mg, so this is going to turn positive underneath the square root, which is good. I just want that number though. What is that number?
You probably don't want to square root it right now.
No, don't square root it yet.
Okay, let me fix that.
What is it?
I got about 4.4 times 10 to the 7.
4.4 times 10 to the 7th, okay. All divided by k, which is still the 50,000. Okay, so that's newtons per meters. Okay, so now let's think about this for a second. Outside in the numerator, actually the denominator is positive, so I don't want to worry about it. Up top, I have outside is negative, and then plus or minus, and then I'm going to square root this giant number. So if I do the positive case, I'm going to wind up with a positive result because this is going to be bigger than 450, okay? If I do the negative case, I'm going to wind up with a negative result. So then the question is, well, what do I want? Do I want the positive results or do I want the negative result? Given that we are compressing the spring, which one do we want?
Negative.
The negative result, yeah. So we're going to ignore the positive case and just go ahead and square root this number and do negative 4, what is it really, 440 something? 441 minus whatever this is, and then divide by 50,000, we'll have our answer, okay? So what do you get? Okay, so this winds up being negative 0.111.
Yeah, and then there is 476.
Okay, great. So meters, right?
Yeah.
So it's 11 centimeters, 11.1 centimeters. Compression. And then you said that this number is actually wrong. It's 2.2 times 10 to the 7th?
2.6, 2.7 times 10 to the 7th.
2.7 times 10 to the 7th. Okay, just to make sure everything's right. So now, that's how much we compress the springboard. Now the second part says, how much time does it take for the board to fully compress? So how can we come up with a time? Let me ask you this, how much of a cycle have we gone through if we compress the springboard down to its maximum compression?
That would just be half.
Is it half of the full cycle?
A quarter.
A quarter of the full cycle? Yes, because if you think about what a wave looks like, so we're going to compress this, okay, now it's at its maximum compression. Now it's going to come back, but it's not going to stop right there. It's going to go through and then turn around to a maximum extension and then come back, and that's one full cycle. So where did we compress it? Right there. That's 1/4 of its full cycle, okay? Now if we think about it that way, and then we think about her, frequency or period, we can calculate the period or the frequency, it doesn't matter, and then come up with 1/4 of the time it took, right? Okay, so what do we do? The frequency, I gotta change colors here, I'm getting confused. The frequency is what?
We could use our 1/2 pi times the square root of k over m.
Or we could use the period and have seconds already, right? So let's do that. Let's get rid of frequency and let's just go with the period this time. Calculate the period and then we need 1/4 of it. So the period, 1/4 of the period is going to be equal to 1/4 of its 2 pi times the square root of, is it m over k or k over m?
M over K.
M over k. And we know all of that. So now we have 1/4 times, actually we could just say 1/2 times pi. So we have pi over 2 times the square root of the mass of this gymnast, 45 kilograms, divided by 50,000 newtons per meter. What do we get?
0.047124.
0.47 seconds. Good. Okay, a pretty complicated problem, but if we do it with energy, it actually becomes a little bit easier. In fact, I'm not sure we could do this without energy. Okay, the last one. 4 mass spring systems have masses and spring constants shown. Rank in order from highest to lowest the frequencies of the oscillation. So what does this depend on?
The coefficient in front of our.
Yeah, the K and the M, right? That's the only thing that can change the frequency. So the frequency equation is 1/2 pi square root K over M or M over K?
K over.
K over M. Okay, so the only thing that changes between these 4 oscillators is the K and the M. So we don't have to worry about the 1/2 pi, we don't have to worry about the square root. All we have to worry about is what is the ratio of K to M, okay? So in A, the ratio of K to M is K over 4M, so it's 1/4. In B, we have 1/2 K over M, so here we have 1/2. So this is 1/4, this one's 1/2. K over 2M, so this is gonna be K over 2M. This is a ratio of 1/2. And then finally 2K over M. This is a ratio of 2. So from highest to lowest, the frequency is going to be the biggest number to the smallest number. So that's going to be frequency of D is the biggest. And then B and C are the same. So we're going to go frequency of B equals the frequency of C, or C and B, either way. And then finally frequency of A is the least. Okay? Good. And the section's done.